In this video, we'll be going over the practice final exam. Let's start with questions 1 and 2. The central limit theorem states the sampling distribution of the sample mean is approximately normal under certain conditions. Which of the following is a necessary condition for the central limit theorem to be used? So the central limit theorem specifically only discusses when states that if you have a large sample, if n is greater than or equal to 30, then the sampling distribution of x bar is also normal. The only option that talks about a large sample is option D, so that is our final answer. For number 2, it says also related to the stuff in section 4.8 on the sampling distribution of x bar. It says here that we have a sample of 64 measurements. It's selected from the population, and the population has an average of 65 and a standard deviation of 12. Find mu subscript x bar and sigma subscript x bar. So mu x bar, remember, is just the mean of the sampling distribution. And sigma x bar, which we also call the standard error, is the standard deviation of the sampling distribution of x bar. So just to recall here, mu x bar was just equal to the population mean, and sigma x bar, or the standard error, was sigma over the square root of n. So let's just use these formulas. Well, in the story, it says mu is 65, so mu x bar must be 65. Okay, so sigma x bar is sigma over square root of n. Sigma was 12, and n was 64. So we're doing 12 divided by the square root of 64. So I'll just take out a calculator and do 12 divided by the square root of 64, and that gives me 1.5. So the standard error of this distribution is 1.5. Question 3. The average score of all golfers for a particular course has a mean of 61 and a standard deviation of 4.5. Suppose 81 golfers played the course today. Find the probability that the average score of the 81 golfers exceeded 62. So this is kind of similar to what we did in section 4.5, where we're going to use the normal distribution to calculate probabilities. The only difference between this one and the one we did before is that we're talking about x bar. We're talking about a sample average. We're trying to find the probability of sample average is more or less than a number. All right, so for that we're going to need, let's see. We found that the average for the population is 61. That's our mu. And the standard deviation of the population is 4.5. Now, for us to use this, we actually don't need mu and x bar. We don't need mu and sigma. We need the mean of our sampling distribution of x bar, which, if you remember, is actually just the population mean mu, same as what question 2 showed. And so that's going to be 61. And sigma x bar is just sigma over the square root of n. And so that's 4.5 divided by the square root of n, which was 81. Okay, so 4.5 divided by the square root of 81 is just 0.5. And these numbers don't always work out so nicely, they just happen to for these examples. All right, let's draw what we know. So we know that the sampling distribution of x bar is going to be normal. And again, this is the sampling distribution of x bar here. And we know it's normal because of the central limit theorem, what question 1 went over. We know it's going to be centered around 61 because it's centered around the mean, and the mean is 61. And we know it has a standard deviation of 0.5. We can't exactly use that yet, but we will when we calculate the z-score. All right, so we want to find the probability that a score exceeds 62. So let's draw a line at 62. And we need to find the z-score associated with this. Oops, sorry about that. All right, so let's do that. So let's see, nice clean spot over here. So our formula for the z-score for a sampling distribution is just x bar minus mu x bar over sigma x bar. Or if you want, you can use the formula x bar minus mu, because mu x bar is just mu, divided by sigma over the square root of n. Either one will work. All right, since we already figured out what mu x bar and sigma x bar was, let's use this first version of the formula. Let's see, so our sample average that we want to find the z-score for is 62. Mu x bar, we already figured was 61. And sigma x bar is 0.5. So 62 minus 61 is 1. 1 divided by 0.5 is just 2. And again, you can use a calculator for this as well. So the z that I'm interested in looking at is 2. So I'm just going to go to the z table and look up 2. All right, so I looked it up on the table, and it shows, remember the table shows the area between 0 and z. And it's showing me that this area here is 0.4772. We actually want to know this area here, because we want to find the probability that an average exceeded 62. So to do that, we know half the curve is to the right of 61, so just do 0.5 minus 0.4772, which gives you, let's see, 0.5 minus 0.4772 gives me 0.0228. And so that's our answer. All right, next question. By the way, this is actually, just a quick note, this is actually the exact same thing as finding a p-value for a right-tailed hypothesis test where our HO is mu equals 61 and HA is mu greater than 61. So you might recognize this from what we did in chapter 6 on hypothesis testing, because this is actually the math behind what we do for hypothesis testing. All right, for number 4, we're asked to find the critical value, which we call z subscript alpha over 2 when we're dealing with confidence intervals. That corresponds to a 95% confidence interval. You might actually have these numbers memorized because there's only a few numbers that we keep recalling for these critical values for large sample confidence intervals. But this will be on your formula sheet. It's commonly used z-values for large sample confidence intervals. So we want to find let's see, we have a 95% confidence interval, so we're looking at this line right here, and the z-value associated with it is plus or minus 1.96. So that's our answer. You could also get this line from the very last line of the t-table, because remember the very last line of the t-table are the z-values. But you just have to make sure to go down the column that's subscript 0.025, because that's alpha over 2. All right, but the easiest way is just look at this table and get the answer. For number 5, we have a random sample of 150 students, so that's our n. They have a test score average of 70, so that's coming from a sample, so it's x bar, with a standard deviation of 10.8. Oops, sorry about that weird drawing there. Standard deviation of 10.8. Find the margin of error if the confidence level is 0.99. Okay, first off, a few things we have to do. The formula for a confidence interval, remember, is x bar plus or minus the margin of error. All we care about is the margin of error part of this. We don't care about the rest. So the margin of error, let's see if so here's our formulas. We have x bar plus or minus this thing, that's one formula for margin of error, or x bar plus or minus this thing, and that's another form of the margin of error. We actually just want the second one, this one, because we're given a sample standard deviation, not a population standard deviation. So that's the formula we want to use. So we have that our margin of error is equal to a z-value times s over the square root of n. Okay, we need to find the z-value. We know that we're dealing with a 99% confidence interval. So pulling up the numbers like we did before, here's our 99% confidence interval, and the z-value associated with it is 2.575. So let's plug that number into our formula. So we have 2.575 times s, which was 10.8, divided by the square root of n, which was 150. So now I'm just going to use my calculator And let's see, 2.575 times 10.8 divided by the square root of 150 gives me 2.27. All right, and that's answer D. All right, one quick note here is the reason why I'm using Z instead of T is that we had a large sample. If this number was like 20 instead of 150, we would have to use T subscript alpha over 2 and use the T table instead. So again, we were able to use the Z values here only because we had a large sample. And I was nice, and on the formula sheet, I even put that in there. So there's a hint on the formula sheet that you should only be using these Z's for large samples. Okay, for number 6, we have a random sample of 56 fluorescent light bulbs. So this is our N. They have a mean life of 645 hours. Since it's coming from our sample, that's our X bar. And a standard deviation of 31. And again, this is coming from our sample, it's an S. Construct a 95% confidence interval for the mean of the population. All right, so let's pull up the information again. We're going to be using the second formula here to generate our confidence interval. These formulas are pretty much the same, except for that one has S, one has sigma. We're using S because we were given S, not sigma. But other than that, it's pretty much the same thing. So let's plug in our numbers. So our sample average was 645, plus or minus. Our Z value for a 95% confidence interval we saw before was 1.96. And our S was 31. And our N is 56. Now, a quick note, I might be nice on the test, and I might just have this as the answer, where you just plug in the numbers and actually do the calculation. Or maybe I'll have you calculate the margin of error part, but I'll leave it as 645 plus or minus the margin of error. And to save you, I'm trying to be nice to save you some time. I might have you just calculate the whole interval, but don't freak out if the answer is written like this. Sometimes when I try to make a question easier, it actually is harder for my students. So again, be aware that you just double check if it's multiple choice, that you don't do extra work that you don't need to do. All right, so for this one though, they actually gave the whole interval, so let's actually calculate the whole interval. All right, first we have to tackle the margin of error because of order of operations, addition and subtraction come last. So we're going to do 1.96 times 31 divided by the square root of 56. And that gives me approximately 8.1. So we're going to do 645 plus or minus 8.1. All right, let's see, 645 minus 8.1. I like to do the subtraction first. So that gives me 636.9. And then we have 645 plus 8.1, which gives me 653.1. So that's our answer, and that matches up with answer B. One quick note here, I don't know if you've noticed this, but this is actually kind of a poorly written multiple choice question. Since we know our confidence interval is X bar plus or minus a number, X bar has to be in the middle of our confidence interval, and X bar was 645. None of these other intervals even include 645, so it had to be answer B, and you could have done that with very minimal calculations. I'll try to be more careful of that on your final, so you won't be able to take that shortcut. But if you see a shortcut, feel free to take it. All right, for number 7, in order to set rates, an insurance company is trying to estimate the number of sick days that full-time workers at an auto repair shop take each year. A previous study indicates that the standard deviation was 2.8. So this is from a previous study, not our sample. So that's a sigma. How large of a sample? So they're saying, how large of a sample do we need? The question is, we don't know N, we want to know it. This is asking us what's the minimum sample size. So we don't know N, we want to know it. That's supposed to be a question mark there. So how large of a sample must be selected if they want to be 95% confident that the true mean differs by the sample mean by no more than 1 day? All right, so remember when you do your calculation for a confidence interval, it's X bar plus or minus some margin of error. So we're adding and subtracting the margin of error. And here they're talking about we're adding and subtracting 1 here. So that means this 1 day, that's our margin of error. So we have sigma, we want to know n, we have a margin of error. Here are the 2 formulas that relate. The book actually gives 3 different formulas for determining the minimum sample size, but these are the only 2 I really want you to know. This first one where it says n greater than or equal to z times sigma over e squared, this is what we're going to do if we're doing a confidence interval for mu. And the second one is what we're going to use if we're doing a confidence interval for proportions. Notice that there's no sigma in here anywhere. So we're going to use this first formula since we're talking about doing a confidence interval for the average number of sick days that employees take each year. Plus we're given a sigma, so it has to be this first one. So we need to know the z, we need to know sigma, we need to know e. Well, we know sigma and e, but we don't know z yet. Well, it's talking about a 95% confidence interval. So again, from the table we saw before, that means our critical value, z, has to be 1.96. So using this formula, it's just going to be 1.96 times sigma, which was 2.8, divided by the margin of error, which is 1. And then we're going to square it. Just be very careful with this calculation. It's pretty common for my students to actually get the math of this right, but then forget to square the number or forget to round it up. So when I do this in my calculator, 1.96 times 2.8, I get 5.448, and then I want to square that, because it says to square it, and I get 30.1 approximately. It's actually 30.118144, but 30.1 is fine. So because we're trying to find out the minimum sample size, we need at least 30.1 people. We can't take 0.1 people, so we're going to have to round this up, and it's going to become just 31. So that's our answer, option B. For number 8, it says find the critical value, t subscript alpha over 2, for a confidence level of 95%. Sorry for writing C equals, I meant confidence level, equals 0.95, and n equals 16. So we're going to need to use the t-table. Notice here, though, that the t-table is asking us for degrees of freedom, not sample size. Our formula for degrees of freedom, which I'm not going to actually include on the formula sheet, I don't believe. So degrees of freedom is just n minus 1. So just remember to subtract 1 when using this table. So let's see. So our degrees of freedom is 15, and our confidence level is 95%. So if our confidence level is 95%, that means alpha is 1 minus that. So 1 minus the 0.95 gives you 0.05. So our alpha value is 0.05. But remember, our confidence interval is two-sided, so we are really looking for an alpha over 2 value. So we're going to do 0.05 divided by 2, which is 0.002, which is 0.025. Sorry, I got cut off there a little bit. All right, anyway, so we're going to go down the 0.025 column right here. So find where those match up, and you get 2.131. And so our answer is option A. Okay, let's go on to the next question. We have here that we have a random sample of 40 college students that has a mean earnings of blah, 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 standard deviation of this, determine whether the normal distribution or the t-distribution should be used or whether none can be used. All right, for this, this question is really just asking you to remember the rules. And here are the rules. You can use the normal distribution under 2 cases. Either if we have a large sample, which is usually, what we're looking for, or in one particular case, if you have any sample size, so even a small sample, if the population is normal and you know sigma. I'm not a big fan of testing on this one, extra condition in parentheses, but basically, if you have a large sample, you can use the normal distribution. You can use the z distribution. All right, you can use the t distribution if you have a small sample, as long as the population is normal. We need that because the central limit theorem doesn't apply. And you also have to have sigma be unknown. So in other words, we're using S instead of sigma here. All right, and then the last case is you can't use either the normal distribution or the t-distribution if you have a small sample, because the essential limit theorem doesn't apply, and if you don't know the population's normal, because then you have no idea what the sampling distribution of X bar looks like. All right, long story short, if you have a small sample and the population's not normal, you can't use either the Z or the t-distribution. So let's see, we have here a sample size of 40. That's a large sample. So if it's a large sample, you know that we can use the Z distribution. So the answer is option B. For question 10, it says construct a 95% confidence interval for the population mean. It says assume the population is normal. We have to do that whenever we have a small sample, which we do. Our sample size is only 16. So we have a random sample of 16 light bulbs with a mean life of 645, that's our X bar, and a standard deviation of 31. Okay, so let's use our formula. Since we have a small sample, and we can use the t-distribution because they said assume the population is normal. So it looks exactly like our other formula, except we have t instead of z in here. All right, so let's do this calculation. Well, actually, first let's pull up the t-table because we know s, we know n, we know x bar, but we need to find what this t is. Since we are using a 95% confidence interval, we discovered before that's going to be t subscript 0.025, and because our degrees of freedom is our sample size is 16, our degrees of freedom is n minus 1, so that's 16 minus 1, which is 15. All right, so using these two pieces of information on the t-table, oops, sorry, I lost my t-table. Actually, this is the number we got before on the t-table. Let's go back for a moment. Right, t subscript 0.025, degrees of freedom being 15, we found that already to be 2.131. So in a way, this is a continuation for number 8. That's just a coincidence, though. I'll try not to do that on your actual test. So we have, go back. Okay, so we have 2.131 as our t, our critical value. And again, we just got that off the t-table with degrees of freedom of 15 and an alpha over 2 value of 0.025. All right, so let's use the formula. Our sample average was 645. And we're going to add and subtract the margin of error, which is just 2.131 times S, which was 31, over the square root of n, which was 16. All right, so I'm going to use my calculator here. So again, I do the margin of error first. So 2.131 times 31 divided by the square root of 16. That gives me 16.5. So I'm really doing, let's find a nice clean spot here, 645 plus or minus 16.5. So let's see, 645 minus 16.5 gives me 628.5. That's my lower bound. And my upper bound will be 645 plus 16.5, which is 661.5. Okay, which one matches? That's option D. So that's our answer. For question 11, it says, when 435 college students were surveyed, 120 said they owned a car. Find the point estimate for P, P being the population proportion of students that own their own car. So our point estimate for P is P hat, and P hat is just the number of successes divided by N. And again, this is really what you would do even if you never took this class. If you want to find the proportion in a sample that does something, you find the number that do something divided by the sample size. We're kind of almost complicating it by putting a formula here. So just do 120 divided by 435, and this gives me 0.27586. If you round that, that's 0.276. Sorry, let me write these numbers here. So we have 120 divided by 435. which gives me approximately 0.276, which is answer B. For number 12, we're told that we have a survey of 280 homeless people, so that's N, and 63 were veterans. So that's our number of successes, I'm guessing. So let's construct a 90% confidence interval for the proportion of homeless people that are veterans. All right, so our formula for a confidence interval for proportions is down here. Sorry, I'm having some pen issues. All right, I think it's all good now. All right, so we know our p, well, we can figure out our p hat value. It's just x over n, just like we did in the previous one. We need to know z. We know we can figure out p hat pretty easily. Once we figure out p hat, we know q hat's just 1 minus that. And n is just the 280 we've already figured out. So we need to find what the z is. Oops. All right, so I'm going to have to go back a little bit and flick several slides here. Forgot to include it on this slide. All right, here we go. So if we have a 90% confidence interval, which is what we were told, the z associated with it is 1.645. So let's use that number for our z alpha over 2, our critical value. All right, there we go. Okay, so our z alpha over 2 is just 1.645. And again, I just got that from the table. All right, we also need to find our p hat value. And p hat is just x over n, so that's 63 divided by 280. So 63 divided by 280, again, I'm using my calculator, is 0.225. And this is actually not rounded. It just works out nicely. Try not to round too much at this step. You don't want to really round too much until towards the end of your calculations. But I didn't have to round here, so no big deal. All right, so our confidence interval is going to be, oh, and by the way, if p hat is 0.225, that means q hat is just 1 minus that. So 1 minus 0.225 gives me 0.775. So I need that in my formula as well. So our formula, using these numbers in my formula, we get p hat was 0.225 plus or minus z, which is 1.645, times the square root of p hat, which is 0.225, times q hat, which was 0.775, all over our sample size, which we established was 280. So using my calculator, I'm going to do what's inside the square root first. So I'm going to do the square root of 0.225 times 0.775 divided by 280. Make sure all of this is under the square root. I get 0.024955, etc. I'm going to take that answer and multiply it by 1.645. And I get that the margin of error is approximately 0.041. So I get 0.225 plus or minus my margin of error, which is 0.041. Okay, so let's see, 0.225 minus 0.041 gives me 0.184. 0.225 plus 0.041 gives me 0.266. So that's my answer. Let's see if I can find it. That's option A.